general relativity step by step. I was making the observation last time that to me relativity is a general relativity at least, is a mathematical theory which happens to have physical applications. And I'm going to adopt that stance through the whole of this course. However, we've developed this mathematics and I'm going to use it. We've got all sorts of results here about coordinate independence. So I was making the observation that covariant differentiation is specially set up so that it doesn't care what coordinate system you use. So I'm going to have to set up a coordinate system for our peculiar specialization into a four-dimensional space where the speed of light is constant for all observers, and we've got the equivalence principle, because if I'm bothered by stuff that's happening outside with monsters and black holes, there's my fish, attack me, I can just build my elevator and ignore it. Temporarily perhaps, but I can ignore it. So I need to set up a coordinate system. So here's me, and I'm floating in interstellar space. There's no gravity to worry about, no monsters. And I'm going to set up a nice coordinate system in terms of this regular three-dimensional grid which I've got. I won't be able to draw it very well. Oops. I won't be able to draw it very well, but it carries on in all directions. There we go. Massive coordinate system, and it's made out of girders or something. And at each intersection, I've got a little clock. I've got a little clock which is running, and I can check that they're all running the same time. And if I'm at a particular time here, I can cruise along here, and then I say, well, it's taking me a particular time to get there. So I can check that my clocks are all reading the same universal time for me. So here's me, and here's my coordinate system. Now, just because I can build a coordinate system doesn't mean it's got any meaning. It doesn't mean it's real. It's just a convenient frame. Well, it's quite literally in this case a convenient framework for me to hang an event, for me to be able to explain what an event is. An event is just a time t that it occurs, and an x, a y, and a z, which tell me which of these intersections that it occurs on. And the event can be something that we all agree on. It might be a little atom emitting a photon. It might be a little flash of light. It might be something, two balls, and they hit each other at a particular time and at a particular location. Well, that's great, and I can play games with my physics, and I can do all sorts of things and describe orbits and stuff like that. Well, that's great, but here's my friend. Here he is, and he sits here, and he's on a spaceship. Actually, I'm going to draw him a bit better. Here he is. Oops. Back to mathematics. Let's get back to the four-dimensional world we inhabit. Here he is. Here's my coordinate system, and here's my friend, who is on a spaceship. There he is, and he's sitting in his spaceship, and his spaceship is moving with some considerable speed relative to me. It's conventional to draw these little lines here, but I don't like that convention. At least, it's not that I don't like it, it's possibly misleading. To me, those lines say that the engine of this spaceship is working. The propulsion system is actually accelerating this engine. And that's not the case. I just want a uniform velocity v. I just want a velocity v relative to me. So I'm sitting there in space minding my own business, and this guy is hurtling towards me at speed v, but he's not accelerating as these lines would seem to imply. So I'm going to get rid of those. I'm going to get rid of those. He's moving at speed v relative to me. And here he is, and he's minding his own business, and he can construct his own coordinate system in much the same way that I can construct my coordinate system. So if I see an event here, something that occurs, well, he can describe that in terms of his coordinate system, which is t dash, x dash, y dash, and z dash, in the dashed coordinate system. Sometimes I use dashes, sometimes I use bars, y bar and z bar. So we've got two different ways of describing an event. I've got my system here, and I've got my friend's system who's moving relative to me. Of course, he thinks by the equivalence principle, he thinks he's stationary, and I'm moving towards him. However, because of the equivalence principle, physics should look the same to both of us. Now that's not a mathematical statement, that is a physical observation, and it might be wrong. It just seems to be reasonably accurate. And of course we've got Michelson-Morley experiments and a whole bunch of other things, things like cosmic ray observations, to show us that physics should look the same to both of us, even though we are moving relative to one another. And in particular, the speed of light should be the same for both of us, or we should observe the same speed of light. So I'm going to stop there. We've got a coordinate system, t bar, x bar, y bar, z bar, and I'm going to consider more and more sophisticated and difficult, complicated coordinate systems that make sense near a black hole in subsequent screencasts. But I'm going to stop there. Stop. Coordinate systems. A framework of space. Far away from black holes and monsters. No monsters, no black holes here. We're just trying to understand flat space at the moment. Stop.